calculus and softball. I'm Chloe.
I'm Alex.
I'm Lily.
So the first thing, why did we choose softball? We could have done anything else, why softball? Well, softball wasn't our first idea. Our first idea, this isn't in good order. Our first idea was baking. We realized that is very hard to get measurements, and we didn't really know what we wanted to do in terms of calculus topics with that. So we decided maybe something easier that you could work off of. Well, then we thought archery. That also turned out to be very difficult because things are moving very fast.
Too fast.
Way too fast and too small. So we moved from there to government spending because we found a lot of information. We realized there was nowhere to go there. We then went to the atomic bomb.
But then Benson pointed out that we might get blacklisted for like looking that stuff up.
So we had to skip that too. And then we went to parachutes, realized drag is disgusting because it deals with a square velocity, which affects acceleration, which affects velocity, and the whole thing. Bad idea.
So, smiley face softball.
And though we didn't need it, I took a video of Chloe hitting a ball. It's in the slideshow now. Yeah. Perfect end. That is how we got data. Guess we're playing again. Okay.
Yeah.
So the first thing that we needed to do was to make a position function. We realized that a function y in terms of x wouldn't really make sense because that's saying that the height is based off of the horizontal distance, which we know is not true. So we decided that parametric functions needed to be used. A parametric function, if you don't know, is where the x and y coordinates of the points are affected by two different equations. So here our x coordinate is affected by 11.436t, and the y is affected by 0.914 plus 9.898t minus 4.9t squared. This just gives you the position of the ball at any t point. So you just input t into these equations, and as long as you're inputting the same t, you get the exact point over the whole curve.
Okay, so I was like, we need a distance formula, but that doesn't really work out for in like terms of t, like the path of the ball. So I was like, let's stay up really late because Mr. Kruger said parametrics. So I stayed up really late one night just researching random stuff and found a good equation for speed. So basically you take your x of t function, the derivative of that squared plus your y of t function squared, or the derivative of your y of t squared, and that gives you the speed, because it's like here's a triangle and it's finding this. So it's basically finding the speed at every point. And then using that, I figured out about when the ball hit 0, or for the height, and integrated on that interval to get a path of the ball distance of 27.081 meters.
Alright, so here you can find the average speed using these fancy equations and stuff. So you just need to find the total distance first from before and divide by the overall time it took to the overall time the ball was in the air. So you get an average speed of 12.847 meters per second or 28.738 miles per hour.
Extrema. So when you're looking at extrema of like the max height of the ball, you only have to look at your y of t function because that's your height. And it doesn't make sense to include your x of t function because it's already going to just be on the bottom. It's going to be a constant anyway. So you take the derivative of your y of t function, you get a time of 1.01. Then I basically did extreme value theorem and stated that you have your two endpoints on the closed interval, and both of those obviously aren't that, so you use your critical of numbers, figured out that it was increasing and decreasing, so I know that time is at the time where our relative, or our extrema is, and then I inputted that into the original y of t function to get a max height of 5.913 meters.
This is where I decided to have fun. We needed, our very first thing at the very beginning, we decided softball. We wanted to figure out what topics can we do. We found extrema, we found speed pretty quickly, we found distance traveled pretty quickly, and I wanted to do something with related rates. I didn't know what I was going to do, but I thought, hey, the velocity is changing, and even though the x velocity is going to be constant without air resistance, the y velocity will be changing because it's going up and down, and that gravity is going to accelerate and decelerate the ball. So what I decided to do was find the rate at which that velocity is changing. So to do that, I first had to start with a velocity function, just based off a Pythagorean theorem. I then had to differentiate that function, which looks kind of gross, but wasn't too bad. I was saying it's just chain rule. The only reason it looks so bad is because I have the velocity in the y direction and velocity in the x direction, and then I had to differentiate them in terms of time. So I got a whole bunch of different smaller related rates that I had to go and find eventually, but it wasn't too bad. So this is your first step. This is just solving or differentiating the square root and then chain rule, and then I simplified it, even though it still doesn't look very simplified. But this is actually a pretty workable equation. When you use that then and just input all your values, you'll see this top part here cancels out because of the 0. And all you're left with is this first term and this under term. And that gets you to that function. You could then use that function and input any time value and find the rate at which the velocity was changing. So though it seems, I want to call it acceleration, but that almost doesn't seem like the best way to put it, because if you were to just think of the acceleration of the ball, you think of just gravity itself, because that's the only thing affecting the ball. And this is actually looking at the change of the overall velocity instead of just the velocity in terms of the y direction that gravity would give you. I ended up using this equation later on to form vectors to visualize what I'm talking about here, but I'll get to that once I get there. Next thing I want to do is the rate of change of the angle. Here it gets much worse because you have the inverse tangent, but it worked out about the same way. So I knew that the tangent of theta was equal to the velocity in the y direction and the velocity in the x direction. Then to solve for theta, I had to do inverse tangent, and then if I wanted to find the rate at which that changed, all I had to do was derive it. And it looks nasty, but a lot of it ended up canceling out. So this was your first initial step. I found the rate at which y is changing and the rate at which x is changing, and just inputted those in here in order to cancel out this velocity in the y direction. So that when I worked it out to here, I could then just cancel this v of x out and then distribute that bottom one through. And that gave me a much easier equation. When I then plugged in my v of y and v of x functions that were simply the derivatives of the very beginning parametric functions, I was then able to make an equation to find the rate of change of the angle at any given time that I wanted. Though this seems pretty straightforward on how you would have solved for these, it looked nasty, and because of these numbers being so large, it seems like that's going to give you a number that's way too big, and that's not going to be the proper change. But it does end up, off of trial and error, both the velocity and these rate of change of angle functions gave you the exact change that you needed at any point. If you're working in radians, do not work in degrees. That does not work. But then, using the rate of change of the velocity and rate of change of the angles, I was able to make vectors. Want to go to the next slide? So here, this is your original curve, if you remember from the very beginning. There's a bunch more points because I wanted to make the curve easier to see. But all I did here is took the rate of change of the velocity function, integrated that to whatever point I wanted, and then added the initial velocity to that. So integrating that rate of change function would give you the total change in the velocity at any point, or up to that point, and then adding the initial velocity gives you the total velocity at that point. And then doing the same thing with the angle of integrating it to find the total change, and then adding the initial, I could find the velocity and angle of the ball at any given point over the whole curve. So here I've demonstrated just 5 of those points. vector v, w, a, b, and c. V is from point 0, so the very initial hit of the ball. W is after half a second, A is after 1 whole second, B is after 1.5 seconds, and C is at 2 seconds just before it hits the ground. And you can see, obviously, vectors V and C are the largest because they have the largest velocity in the y direction, and A is at 1 second, just near that extrema that Chloe found as the maximum height, and you can see that the tangent line is almost parallel at that point. So this was another cool way that we discovered you could probably do with extrema, saying that these are just tangent lines given a set magnitude based off velocity. Now we're doing King Kong. We don't really know how we got here, but Benson said before, you know, instead of just doing, we didn't want to just do a normal softball presentation, we thought that'd be boring. So, what if King Kong played softball?
And
Is
that's
the question of the century.
It is. Now, you might be asking, how did I figure all this out? Well, specifically, I used the King Kong from Skull Island, the 2017 remake. In that, he is 104 feet tall, which is about 31.699 meters tall. He is modeled after a silverback gorilla, and that's like based on like the sizing. I made a ratio, and it's about 18.114 times taller than the average silverback gorilla. And so then I used that strength, like I used that multiplier, and then I did like a strength multiplier because we figured out that the silverback gorilla can like bench press like 1,800 pounds. So then I figured out how much he could bench press, which is about this much. And then we rounded, because I wasn't hitting the ball as hard as I could, so I said like an 80 bench press for myself, times by that. And then I did a height multiplier too, so that's like, I hit it about 3 feet tall, so that's how high he hits the ball. If he had hit it at the same angle I did, I hit it at like a 40.877 degree angle. So then I found the velocity, this was my velocity this way, and this would be, I times by the strength multiplier up here to find out King Kong's velocity. Now then I inputted the triangles, so I made little triangles based off of mine, and this is basically like a similar triangle. Same angle, and then that was this velocity. And then I could find the velocity in the y direction and the x direction to make two similar functions to what I had before. With those two functions, I was able to do the same exact thing I did for mine to find the total distance. That is the path of the ball distance, which is approximately to Carson City, Nevada, and back. Not just to there, but back. You have to be specific about that. They're really big numbers, so I kind of worried about scaling, looking at it.
So back to average speed. It's like the same thing as before, but oh gosh. So using the same like derivatives and of the x and y squared equations, you can find the speed by dividing by the total distance. It gets you like, gosh, the average speed like ends up to be 5,190.576 meters per second. So it leads you to 11,610.998 miles per hour, which is just over Mach 15.
Basically, everyone in the like immediate area is dead. Yeah.
Yeah, we found out that a sonic boom that close to you and it going Mach 15, it would tear your lungs apart because of the pressure, and everyone would just die.
Even if like your lungs were like somehow encased, the sheer force of it breaking your eardrums would probably cause such significant damage on your brain you would not survive anyway. And then like if he threw the bat while he was running, it's over. It's earthquake. Just bad stuff is happening. Okay. Here we go again. Okay. So again, I did the derivative of the y function to find out the max height, which is a giant number, 83,000 well. And then I wanted to know how many softball fields he could hit over. Approximately 57, 228 softball fields is how far he would hit in just like the X direction. Yeah, careful. That's like causing damage when it falls too. Better not. If it was a line drive, everyone would just. It's over for you.
Okay. So using the same formulas that I had before, I didn't do the whole derivatives again because it's the same one as before, just different numbers. So this time when you do the rate of change of the velocity, you're using different equations, but it works out the same way, and you can use that in the same way, and I'll show the vectors again later.
Okay, once again, using the same stuff as before, you just plug in bigger numbers and get the rate of change of the angle this way.
Okay, so now, what if you could visualize the vectors, you visualize the magnitude, which is the velocity of the ball, and the angles as vectors again? We realized that, or I realized in my struggle to figure out how vectors work, that this was not a very good idea, because here you can see the whole arc of the whole ball. If you can look over here, you see point B. That is just how I use to mark these points. If you look over here, you see a cluster of 2 letters. That is one velocity and one vector. It is so small compared to the whole arc of the whole graph that I realized that these vectors would look stupid if I tried to put them all over. But I did anyway. So if you were to do these vectors, this is a visualization of the very first vector of just right after King Kong were to hit that ball. This is a little more than 6,000 meters per second, as we found before, at the same angle, at 40.877 degrees. I realized that in doing this, because it's so fast and because gravity has such a small effect on it over this short amount of time, because he hits this thing and it flies for like, what was it, 12 minutes?
Yeah, like.
It's in the air for a really long time.
15 minutes, like, it's gone.
So I realized that in doing these, it has such a small effect that this vector u you see here is from the initial point. That is point 0 when he first hits it, and overlapping here to the point where you can't even see any edges is the first point, the second point, and the third point. So if you go back and you look at that whole big graph again, that tiny little vector is only between the initial point and the first point. And that's that tiny little dot over there. So I realized this is kind of pointless, and I figured out vectors again for nothing. Questions?
Preguntas, lo siento por infarto.
Sorry for the
Honorable
heart
mention.
attack. That's what that says in Spanish.
Honorable mention, Miss Benson. Yes, Miss Benson.